In this video, I want to talk about one of the best ideas I think anyone ever had in physics. Imagine that I have a surface like this three-dimensional paraboloid. It's a surface of revolution. If I took a parabola and spun it around, I would get a bowl shaped like this. Now imagine I put a particle in that bowl. If I put the particle at the bottom, we know there'll be no net force on it. Just imagine this is a bowl sitting on a table. If I put a particle in the bottom, it'll stay there. But if I put a particle some distance from the bottom, say up here, I know that the particle is going to slide down in the steepest direction. Whatever the steepest direction is, wherever that particle might be, it's going to slide in that direction, and the steepness of the bowl at that point is going to determine the size of the force. So we have this surface acting as a visualization tool for both the direction and the magnitude of the force. The steeper the surface is, the stronger the force will be. The direction of the force is always going to be in the most steeply downward direction. What we say in this case is that the force is equal to the slope of some function, but in the downward direction. Now, a feature I'd like to add to this graph is to have some contour lines, like a contour map of some geography. So let's see what that looks like. We've added lines here that are evenly spaced in terms of height. So if we look down on this shape, what you can see is that these are concentric circles for this function. And the function we started with here was that the height, the potential energy function, was equal to 1/2 k r squared, where r is the distance from the center here. And what I hope you can see is that these intervals are these are evenly spaced intervals, but they're getting smaller and smaller as we go further from the center of this coordinate system. So what that means is we can see how steep the function is by looking at how closely spaced these lines of constant height are, which here are circles because this is a function of radius, and these lines, which all have equal potential energy, have a name. They're called equipotentials. And a thing that we can see that's always true is that the force is always going to be perpendicular to equipotential lines. To connect this to something a lot simpler, let's return to a one-dimensional system that we've already seen. Suppose that I have a frictionless surface, and attached to a wall I have a Hooke's law spring, and that Hooke's law spring is attached to a mass, a box of mass m, which can slide without friction back and forth on this surface, and let's suppose that that box is displaced by a distance we'll call x. Now suppose we want to graph the force exerted by this spring. We've already said it's a Hooke's law spring, so I know that the force exerted by it is equal to minus k times the displacement of the spring. Now I'm going to measure distance from the center on an axis called r, and I will call the actual displacement x, a particular value of r. We see that the force as a function of r is minus kr, and I'd like to know how much energy has been stored when we've displaced the spring by a distance x. So we can calculate that. We can look at the work done by this force, minus kr. That work is going to be the integral of minus kr dr as we move from 0 to x, and we can see that that is equal to minus 1/2 k x squared. Now we know that the work done by the spring is equal to minus the work done on the spring. Because of that, the opposite of this work done by the spring is the energy we have put into the system that we have stored. So that is 1/2 k x squared. We can check that this fits the relationship we were talking about with our visualized surface, where we said force in the x direction is equal to minus du dx. Let's take that derivative here. Minus du dx turns out to be here, minus kx. Bringing down that exponent cancels the 1/2, and we have our minus sign from the definition of the relationship. So let's look at that, visualizing this potential energy function. This function here is a nice parabola, so we can see that what we're doing effectively is imagining that this mass, as it moves back and forth, is like a frictionless bead in a parabolic half-pipe. And the steepness of that half-pipe at this position x is what's determining the direction of the force on the particle. So when the slope is positive, the force is in the negative direction. When the slope is 0 right here, there's no net force, which we know is true in equilibrium here at 0. And when the slope is negative, we have a force that is positive. So this is the metaphorical relationship of riding in a frictionless half-pipe or along some shape of surface, and equating that with a slope of that surface that determines the force.